You know how our world is getting smarter all the time? Well, it's not magic. It's actually this invisible web of tiny, intelligent sensors all around us. They're constantly sensing, thinking, and communicating. So today we're going to dive into the secret world and really see how these wireless sensor networks tick.
I mean, just think about that for a second. What if a bridge could tell us it's feeling stressed? Or a farm could tell us exactly which plants are thirsty? This isn't some far-off sci-fi dream. It's the reality being built right now, all thanks to the tech we're about to break down.
So here's our game plan for this explainer. We're going to start with the single most important building block, the sensor node itself. Then we'll see how they team up, check out some of their amazing real-world missions, tackle their #1 enemy, battery life, and finally look at the rules that stop them from all talking at once.
All right, let's dive right in. We're starting at the absolute core of any wireless sensor network, the individual sensor node. And right at the heart of that little node, you've got its brain.
This little guy is the controller. And yeah, calling it a brain is pretty spot on. Just like our own brains, it takes in information from its senses, electronic sensors measuring stuff like temperature or motion or light, and then it has to figure out what that all means and what to do about it.
And this whole process is just a constant, super fast loop. First, the sensor grabs some raw data. Then the controller chews on it, asking questions like, is this normal or is this a big deal? And finally, it makes a decision. Do I just store this data? Do I need to shoot off an urgent message? Or do I trigger an alarm right now? This simple little loop is what makes the entire network so powerful.
Okay, so one sensor on its own is, well, it's kind of like a lonely detective. The real magic only happens when they start working together as a team. So let's look at how these nodes team up using sources, sinks, and signals.
In any of these networks, you've basically got two main players. You've got your source nodes. These are your eyes and ears out in the field, gathering up all the information. You can have hundreds, even thousands of them. And then you have the sink nodes. Think of these as the command center that all the sources report back to, piecing together the full picture from all that data. And get this, a sink doesn't have to be some boring server in a closet somewhere. Imagine sensors scattered all over a forest fire. The sink could be a rugged little handheld device right in a firefighter's hand, giving them a live, real-time heat map of the danger they're literally walking into. That's a mobile sink, and it's a lifesaver.
So how do these sources talk to the sinks? Well, they're smart about it. Sometimes they only speak up when a specific event happens, like a sudden spike in temperature. Other times, they just send out steady, regular updates. They can even work together to draw a map of something, like the boundary of a fire, or team up to follow a moving target.
Okay, enough with the theory. This is where it gets really cool. Let's go see these networks out in the wild, doing critical missions that save lives, protect nature, and just make our world work better.
And the applications are all over the place, and they are seriously diverse. For the military, they can create invisible tripwires along a border. For conservation, they'll let us track animals without ever disturbing them. In our cities, they're the invisible brain managing traffic flow, and in huge warehouses, they're basically the air traffic controllers for a whole fleet of robots.
Let's really walk through that intruder scenario, because it shows you just how smart this system is. So an intruder crosses a line. The first sensor pings, I've got something. As they keep moving, the next sensor in their path wakes up and says, hey, they're over here now. The network sync takes these reports, connects the dots, and in real time can figure out not just where the intruder is, but how fast they're going and which way they're headed.
Okay, so all of these incredible applications, they all run into the exact same massive roadblock. These tiny sensors are often put in really remote places where you can't just go plug them in. This brings us to the single biggest challenge in this whole field, the constant, brutal battle for battery life.
To get it, you just have to look at where the energy actually goes. Sleeping? That uses almost zero power. But the second a sensor turns its radio on, even just to listen, the power usage jumps. And transmitting, actually sending a signal, that is, by far, the most expensive thing it can possibly do. Even just sitting there, with the radio on but doing nothing, drains the battery.
And this right here, this is basically the golden rule for designing these networks. Every single design choice comes back to this one principle. If you want your network to last for months or even years on one tiny battery, you have to be unbelievably stingy about how often you transmit. Every single data packet has to count.
So what's the solution? How do they pull it off? Well, the main weapon they have in this fight is a strategy called duty cycling. And really, it's just a super strict sleep schedule. Instead of staying awake 24/7, the sensor spends almost all of its time in a deep sleep and only wakes up for a tiny fraction of a second to do its job, and then boom, it's right back to sleep.
And this strategy is a total game changer. I mean, look at this. A sensor might only be fully active for 5% of its life, or even less. That other 95% of the time is just pure energy savings. That's how you stretch a tiny battery's life from a few days into several years. It's the absolute key to making these networks practical.
All right, we're almost there. We've got our nodes, they have a mission, they know how to save power. But what happens when hundreds of them all try to talk at the same time? You'd have a massive digital traffic jam. That brings us to our last piece of the puzzle, the rules of the road.
The solution is something called a Medium Access Control Protocol, or just MAC protocol for short. You can think of it exactly like traffic laws for the airwaves. It's a set of rules that every single sensor agrees to follow so they're not all shouting over each other, which would just cause their signals to collide and turn into useless noise.
And there are really two main ways to handle this traffic. On one side, you have contention-based systems. Your home Wi-Fi works like this. Everyone basically just listens, and if it sounds clear, they try to talk. It's simple, but when it gets crowded, you get collisions and a lot of wasted energy. On the other side, you have schedule-based systems, where every node gets assigned a specific time slot to talk. No one else is allowed to talk then. It completely avoids collisions, it's way more energy efficient, and it's perfect for most of these wireless sensor networks.
So when you pull it all together, it's a pretty amazing story, right? You start with this one simple node, this tiny brain making decisions. Then those nodes team up to do incredible work, from tracking intruders to protecting wildlife. But none of it would be possible without solving that ultimate puzzle of battery life, using clever tricks like strict sleep schedules and rigid communication rules to make every last drop of energy last for years.
And that really leaves us with one final big question. We're essentially building a nervous system for our planet, giving a voice to the world around us. And as this tech gets cheaper, smaller, and way more powerful, the question isn't if we'll use it anymore, but what we'll choose to listen to. What big problems should these tiny digital detectives help us solve next?